In this lesson, we're going to take a look at some basic differentiation rules. Now, these rules are important because they're going to allow us to evaluate the derivative of a wide range of functions without resorting to the limit definition. So that's going to save us a lot of time and work if we don't have to use the limit definition. Now, keep in mind, though, the limit definition of the derivative is still required to prove all of these results are true. So the limit definition, we needed to study that. It wasn't like what we did was a waste of time, because we're going to use that limit definition to prove these results are true. And that limit definition also gave us an idea of what the derivative is, as being the slope of the tangent line. So let's take a look at our first theorem here. And it states that the derivative of a constant function f of c is 0. So we can write that as the derivative with respect to x of the constant function c is 0. Now, this result makes sense if you consider the graph of any constant function. Like right down here, we have the graph of a constant function. Right here, y equals c. This graph, it looks like it might be the constant function y equals 3. It looks like it's crossing the y-axis at 3. Now, if you pick any point on the graph of this function and you want to draw a tangent line through that point, notice that the tangent line is just the line itself. And it's a horizontal line. So the slope of that horizontal line is 0, of course. The slope of any horizontal line is 0. And so that's true for any point, no matter where we are on the graph of this function. So therefore, our derivative is 0 everywhere. Remember, derivative measures the slope of our tangent lines. Every tangent line here is horizontal, so it has slope 0. So that's why this result is true. We'll prove this precisely in a few minutes using the limit definition, but this is graphically what's going on. Let's take a look at two quick examples. So the first one here, we just want to evaluate the derivative of the constant function y equals 2. Well, all we have to do is write d dx of 2. Well, since that's constant, it's just 0. For the function y equals pi, it's the same thing. D dx of pi is a constant, remember, 3.14159, and keeps going, but it's still constant. That's just 0 because this is a constant function as well. And that's all you have to do. It's pretty simple. Let's take a look at the proof of this result. So we're going to let f of x be a constant, c, and we want to look at the derivative of this function. So df dx is going to be the limit Alright, so we have to go back to our limit definition. Now, if f of x is a constant function, that means that both of these terms right here, this one and this one, they're both c, right? They're just a constant. It doesn't matter what I put in for the x over here, I get back the number c, no matter what x is. So these terms are both c, and so we end up with and that is equal to, right, because the numerator is just 0, c minus c is 0, and this limit is 0. And that's what we had to prove. So therefore, the derivative of any constant function is equal to 0. All right, let's take a look now at another rule. We're going to now consider the power rule. Now this is a really useful and important rule. So it states that for any constant number n, f of x equals x to the nth power is differentiable and its derivative is nx to the n minus 1. Notice how this works. If you have x to the n, and you want to take the derivative of this function, it's telling you that all you have to do is drop the n down in front of the x, and then subtract 1 from the exponent. And that's your derivative. So it's very easy to follow. Let's take a look at an example. So here we want to evaluate the derivative of y equaling x to the third power. And then we want to use that derivative to find the equation of the line tangent to the graph of y equals x cubed at the point 2, 8. And we'll illustrate this graphically as well. Alright, so following the power rule, so we just have to drop the 3 down, subtract 1 from the exponent, and of course that's just going to be 3x squared. So that's our derivative. Now to find the equation of the line tangent to the graph at the point 2, 8, we just have to evaluate this derivative at 2. So we have now, remember f prime is, we'll write f prime out here first. So there's f prime. So f prime of 2 is now going to be 3 times 2 squared, and that is 12. So that's our slope of the tangent line. And the point is the 2, 8 up here. Notice we get the 8 by evaluating 2 cubed. We put the 2 into the original function. That's our y coordinate. And so the equation of our tangent line is then going to be and then that can be simplified to, right? Just distribute the 12x minus 24, bring the 8 over, 12x minus 16. And so there is the equation of our tangent line at the point 2, 8. And you can verify all of this graphically. You can graph on your calculator y equals x cubed. That's the graph of the blue curve here. And then if you were to graph the equation of this line right there, that's the gold line right there. And you see right here at the point 2, 8, yes, it does look like it is tangent right there. Let's take a look at another example. So here we want to evaluate the derivative of the square root of x. So what we have to do is somehow write this function as x to a power in order to apply the power rule. Well, of course, the square root of x, we can write that as, that's just x to the 1/2 power. So our n in this case is going to be 1/2, so f prime of x so we just dropped the 1/2 down in front of the x, subtracted 1 from our exponent, and then this can be simplified as, and then this can be further simplified as, and there we go, we have the derivative of the square root of x, being just 1 over 2 root x. Let's take a look at this one. Y equals 1 over the cube root of x. So once again, we have to write this as x to some power n in order to apply the power rule. Well, let's write this as, this is going to be 1 over x to the 1/3 power, and that we can write as x to the negative 1/3 power. All right, so this is just another way of writing 1 over the cube root of x. So therefore, f prime, or dy dx, we'll use some different notation to get you used to that. So dy dx in this case is going to be, we drop the negative 1/3 down, x to the negative 1/3 minus 1. So that's going to be And there's our derivative, negative 1/3 x to the negative 4/3. Or we could write that as, you might see it written in different forms, we could write that as negative 1 over 3x, 3 times x to the 4/3 power. So there's another way to write it. And that's it. That's all you have to do to use the power rule. Now, the proof of the power rule, that's a little bit involved, so we're going to save that for another video. Now let's take a look at the constant multiple rule. It states that if f is a differentiable function and c is any real number, it's going to be a fixed real number, then c times f of x is differentiable, and the derivative of c times f of x is c times the derivative of f. So in other words, you can pull the c just out in front of the d dx, and then you only have to worry about taking the derivative of f. So you just take the derivative of f and multiply it by the c. You may also see this written as, so you may see it written like this. It's the same thing. The derivative of c times f is just c times the derivative of f. All right, let's take a look at a few examples. So here we want to evaluate the derivative of 5 times the square root of x. Now, let's first of all realize that we can write this as 5 times x to the 1/2 power, of course. So then dy dx is going to be d dx. And now we can just move this 5 outside the d dx. And now we can just apply the power rule here. Remember, we get this negative 1/2 by subtracting 1 from the exponent over here when we differentiate. So that's where that negative 1/2 comes from. And then this can be cleaned up as right there. And there is our derivative. So notice how we can basically, what we do is we just sort of ignore that 5, take the derivative of x to the 1/2, and then just multiply the 5 by it. So that's all we're doing with the constant multiple rule. Let's take a look at this one. Let's find the equation of the line tangent to the graph of this function at the point 1, 3. All right, so remember, to find the equation of the tangent line, we need the slope of the tangent line. Well, so that's the derivative. So we have to evaluate the derivative at the point 1. That'll give us the slope of the tangent line, and then we can find this equation. So we have to take the derivative. So differentiating this function, let's write this function as, now we can just ignore that, sort of move the 3 out in front of the d dx, or just sort of ignore it and take the derivative of x to the negative 2, then multiply by the 3 again. So there's our derivative, and then we can clean this up as, and there we go. So there's dy dx, but now we still have to find the equation of the tangent line. Okay, well, we are given that the point is, we're given the point being 1, 3. Now we can find the slope by evaluating dy dx at 1. And when we put 1 in here, we get negative 6. So there's the slope of our tangent line. So the equation of our tangent line is then going to be, there's the equation of our tangent line. And we can simplify that too. See, we're going to get 6. Negative 6 times negative 1 is positive 6. add the 3 over, plus 9. And that's the equation of our tangent line. All right. Now let's take a look at the proof of the constant multiple rule. So we want to start with the derivative of and we need to justify that we can move that c out in front of the d dx. So let's go back to our limit definition. Alright, so that's our limit definition for the derivative of this function. Now notice we can factor the c out like this. And then by properties of the limit, we can move this constant out in front of the lim. That's one of our properties of limits. And what we have here, this part, is just f prime of x. And so we have that this is equal to c times df dx. And that's what we wanted to prove. So we've just justified that the c can be moved out in front of the d dx. And that's the proof of the constant multiple rule. Now let's take a look at the sum and difference rules. So these rules state that if f and g are differentiable functions, then f plus g of x is differentiable as well as f minus g of x, and we can follow these rules. The derivative of f plus g is going to be the derivative of f plus the derivative of g. So in other words, notice how we have basically can actually just take the d dx and distribute it in front of the f and in front of the g. That's basically what this rule is doing. And the same thing with minus, exact same rule. Derivative of f minus g is going to be the derivative of f minus the derivative of g. Let's take a look at a few examples. So the first one here, we want to evaluate the derivative of this function, x cubed plus x squared plus x plus 5. Alright, so f prime, or df dx, that's going to be d dx of this entire function. And now by the sum and difference rule, we can distribute the d dx to each individual function here. And now we can just use the power rule and constant function rule to evaluate the derivative of each term. Now notice here the derivative of x, that's just going to be 1. Let's just do that up here. Note that if I want to evaluate d dx of x to the 1 power, notice we drop the exponent down. That's going to be 1 times x to the 0 power, and any number to the 0 power, that's just 1. Alright, so that's a special function there to take note of. The derivative of x is just 1. And then the derivative of a constant, that's just going to be 0. Alright, so then this of course is just, and there is our derivative. Now once again, of course, I went through these steps in detail to show you how you're using each rule when you're differentiating this function. Of course, you can just jump right down to this answer. Once you've done this a few times, it's fairly easy. You can just state that f prime equals the derivative of the first term plus the derivative of the second term plus the derivative of the third term, and then plus derivative of the last term is 0, and there's your answer. So you notice how we just didn't go through all these steps. I'm just going through these to illustrate how you're using each rule. Let's take a look at another example. So the derivative of this function So what we can do now is distribute the d dx to every term. So that's by the sum and difference rule. And then we have constants here that we can move out in front of the d dx. All right, and now we can just evaluate the derivative of these terms using the power rule and the constant function rule. Now when I drop the 3 down here, and then I'm going to multiply it by 4, that's going to give me 12x squared. 5, when I drop this 2 down, multiply it by the 5. The derivative of x is just 1. And then the derivative of pi is 0, because that's a constant, so we don't have to put anything there. And there is our derivative. Notice once again, once you do this often enough, you don't need to go through all of these steps. Right here, if you just read this off, f prime, derivative of the first term, ignore the 4, just differentiate x cubed, drop the 3 down, but you do need to multiply it by the 4, so it's going to be 12x squared. The 5 just hangs around, differentiate x squared and multiply it by the 5, so it's going to give you 10x. 3, just multiply 3 times the derivative of x. Derivative of x is 1. Derivative of pi is 0, so you don't have to add anything here, and there's your answer. But this is showing you how over here how you use each rule. All right, let's take a look at one more example. All right, well, I lied. We actually have 2 examples here. So the first one, we want to evaluate the derivative of this quotient. Now, if you had calculus before, you might be able to recognize that you can use the quotient rule on this function to evaluate its derivative, and that's certainly true, but we haven't studied the quotient rule yet, so we don't want to use that. So what we have to do is rewrite this somehow so that we can use the power rule, the constant multiple rule, the sum and difference rule. So we're going to rewrite this as follows first, before we try to evaluate its derivative. And now, let's try to further rewrite this as the first term is just going to be x squared over x, plus, this is going to be 3x to the negative 1/2 plus 4x to the negative 1. And now we can differentiate this using our rules. So f prime then is just going to be the derivative of x, which is 1, plus the derivative of 3x to the negative 1/2. All right, the 3 just hangs around. We drop the negative 1/2 down, and we subtract 1 from the exponent. The derivative of this term, the 4 just hangs around. We differentiate x to the negative 1, drop the negative 1 down. And then we can clean this up a little bit. So let's write this as and there's our answer. And you may also see that written as that's just an alternate form that you could see. Either one is perfectly acceptable. All right. And just keep in mind again, the derivative of x is always 1. Always just keep that in mind. You can certainly see that coming out from this form after all. Dx over dx. Think of it as like a number, over the same number. That's just 1. All right. Now let's take a look at this. Let's find where f of x equals x squared plus x minus 3 has a horizontal tangent line. All right, well, a horizontal tangent line has a slope equaling 0. So in other words, we need to find where f prime of x is equal to 0, right? Because the derivative measures slopes of tangent lines. So if our tangent line is horizontal, that means its slope must be 0. So that's where f prime is going to be 0. So we need to just take the derivative of this function. Well, the derivative is just, right? The derivative of x squared, drop the 2 down, subtract 1 from the exponent, so that's just 2x. The derivative of x is just 1. And now we set that equal to 0, and we solve that for x. And that's going to tell us that x is negative 1/2. And so that's where our derivative is equal to 0. Now, if we want to find the actual point on the graph, that's going to be negative 1/2, f of negative 1/2. And in this case, if I put negative 1/2 back in here for x, I'm going to get negative 3.25. So this is the actual point on the graph where this function has a horizontal tangent line. And let's take a look at the graph to verify this. So here is the graph of this function. And we see that it looks like right about there is where our tangent line would be horizontal. And we see that that looks like it is about the point negative 1/2 and negative 3/2. So it looks like that, yes, we have found where the graph of this function has a horizontal tangent line. Now let's take a look at the proof of the sum and difference rules. So we want to start by looking at the derivative. We're just going to prove the sum rule. The difference rule is exactly the same. And to prove this is the derivative of f plus the derivative of g, we have to go back to our limit definition. Alright, so here's our limit definition for the derivative of this function. So we have f of x plus delta x plus g of x plus delta x, and then minus f of x plus g of x, all of that over delta x. Now what we're going to do is we're going to split this up as follows. So you see all we did here is combine the f of x plus delta x with the f of x, the g of x plus delta x with the g of x, and then we split the fraction apart. So what we have down here is exactly the same as what we have up here. And now what we can do is we can actually distribute the lim to both terms individually. And that's by our limit rule. Alright, and so remember we use the rule that the limit of the sum of two functions is the sum of the individual limits. And now you see this part right here, this is just f prime of x. And this part right here, that's just g prime of x. And so we then have our result that this is the derivative of f plus the derivative of g. And that's what we needed to prove. All right, so that concludes now our discussion on some basic differentiation rules.